Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're covering matrix multiplication, the rules, conformability requirement, and properties. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Ruth's friend and co-PhD student Victor has asked her for help with his dissertation. Victor admits that he's fallen a bit behind in the program and he's trying to catch up. But before he can get working on writing, he needs to first understand how matrix multiplication works. Ruth happily agrees to help get him caught up. She pulls up her chalkboard. Last video we covered matrix addition, subtraction, and scalar multiplication. Those were entry-by-entry operations with a simple conformability requirement. Today we move to matrix multiplication, which is a different animal. The rule for multiplying two matrices doesn't work entry by entry. It works on rows from the first matrix and columns from the second. And the conformability requirement is more specific. The reason matrix multiplication is so important is that it ends up being how we compute things like portfolio returns, how we apply linear transformations, and how we end up setting up systems of equations, and ultimately how we derive the regression coefficient in Module 5. It's the load-bearing operation in the rest of the course, so it's important to understand it carefully. So to better understand things, let's think of an example. Imagine a fund running two strategies side by side. A defensive strategy with 3 positions, and an aggressive strategy also with 3 positions. We can lay both strategies out in a single matrix where the rows are the strategies and the columns are the position slots. The top row holds the defensive returns. The bottom row holds the aggressive returns. So we have one matrix, 2 strategies, and 3 positions each. Suppose Ruth's example matrix R looks like this. The defensive row, position 1 through 3, returns 8%, 4%, and 6%. In the aggressive row, returns are 16%, 12%, and 8%. So R is a 2 by 3 matrix. The question is, if we apply equal weightings to the 3 position slots, how much does each strategy end up returning? Equal weighting means each of the positions gets 1/3 of the strategy's allocation. So we can write that as weight vector W with 3 entries all equal to 1/3. As a column vector, W is 1/3, 1/3, 1/3, 3 by 1. What we're trying to figure out is the return on each strategy if we have equal weights among the 3 assets within them. To do this, we need to get one number per strategy or 2 numbers, the defensive return and the aggressive return. So we need an operation that takes the 2 by 3 matrix R, combines it with the 3 by 1 matrix vector W, and produces a 2 by 1 vector with 1 entry per strategy. That operation is matrix multiplication. Here's how matrix multiplication works. To multiply matrix A times matrix B, the number of columns in A has to be equal to the number of rows in B. That's the conformability rule for multiplication. If A is m by n, then B must be n by something else. The inner dimensions must match. Both must be n in this circumstance. And the product AB ends up being m by p. So the outer dimensions end up becoming the dimensions of the result. In our case, R is 2 by 3 and W is 3 by 1. So the inner dimensions are both 3, so they match. The product RW is going to end up being 2 by 1, so one number for each of our strategies. Let's do now the actual computation. Each entry of the product is going to be a dot product of a row of R and a column of W. Specifically, the entry in row I, column J of RW equals the dot product of row I of R and column J of W. The dot product, which we set up in a previous video, ends up being the building block. Matrix multiplication is just a lot of dot products organized into a result matrix. So let's compute RW. The first entry of the product is the defensive strategy's return. It's the dot product of the first row of R with the weights vector. With each of the 3 positions getting an equal 1/3 weight, the dot product is just the simple average of the 3 defensive returns. So 0.08 times a third plus 0.04 times a third plus 0.06 times a third, which gives us 0.06. So the defensive strategy return is 6%. The second entry of our new matrix is going to be the aggressive strategy's return. So with the same setup, do the dot product of the second row of R with the same weights vector. That ends up being 0.12. So the aggressive strategy's return is 12%. So RW is 0.06 on top and 0.12 on the bottom. So 6% defensive and 12% aggressive. We have 2 strategies, and now we know both of their returns, and we end up representing them with a single vector. Now let's extend the example. Suppose we want to compare two different weighting schemes side by side. The first scheme is the equal weighted one that we just used. The second scheme overweights the most promising position. So 50% for the first position, 25 for the second, and 25 for the third. Instead of running the calculation twice, we can stack both weighting schemes into a single weights matrix W. Here W is going to have two columns, and the first column is the equal weighted vector, so 1/3, 1/3, 1/3, and the second column is the new vector, so 0.5, 0.25, and then 0.25. So W is a 3 by 2. Now we can compute R times W. R is a 2 by 3 and W is a 3 by 2. So the inner dimensions match. So once we get the product, we'll have a 2 by 2, where each entry of the result is the dot product of one row of R and one column of W. The entry in row I, column J, answers the question, what does strategy I return when weighting scheme J is used? The top left entry is the defensive strategy under equal weighting, and we already computed that and we know it's 6%. The top right entry is the defensive strategy under the promising heavy weighting. So this would be the dot product of the defensive row with the column 0.5, 0.25, 0.25. So 0.5 times 0.08 is 0.04, 0.25 times 0.04 is 0.01, and 0.25 times 0.06 is 0.015. Summing these up, we get 0.065, so 6.5%. The bottom left entry is the aggressive strategy under the equal weighting, which we also already computed, and that's 12%. Then the bottom right entry is the aggressive strategy under the promising heavy weighting. This is the dot product of the aggressive row with the same column. If we work through that dot product, we get that the sum is 0.13, or 13%. So R times W ends up being a 2 by 2 matrix. The top row, 6% and 6.5%, and the bottom row, 12% and 13%. Each row tells us how a strategy performs under the two weighting schemes. Each column tells us how a weighting scheme performs across the two strategies. One matrix multiplication answered 4 questions at once. Notice what's interpretable here. Every entry of the result is a portfolio return, and every entry came from a dot product of a returns row and a weights column. The structure of matrix multiplication didn't add anything new on top of the dot product. All we really did is organize a lot of dot products into a clear grid. Notice also what changed between the two weighting schemes. Equal weighting gave 6% defensive and 12% aggressive, but the promising heavy strategy gave 6.5% and 13% for the aggressive. The aggressive strategy benefits more from concentrating on the most promising position, because the spread between the best and worst positions in that aggressive row is much wider. So we know that using the promising heavy weighting is more important for the aggressive strategy. So now that we have our rule clear, let's name the properties of matrix multiplication. There are 5 that are worth knowing. First, matrix multiplication is not commutative. In general, AB is not equal to BA. This is different from regular numbers. Take a small 2 by 2 example. Let A equal 1, 2, 3, 4, and let B equal 0, 1, 1, 0. AB works out to 2, 1, 4, 3, but BA works out to 3, 4, 1, 2. These are different matrices, so we know that order matters. Second, matrix multiplication is associative. Let's say we want to multiply A times B times C. You can group this as either A times the product BC, or you can do the product AB multiplied by C. Either way, you're going to get the same result, and while this is easy to verify, I'm not going to force you to sit through going through an example. Third, matrix multiplication distributes over matrix addition. A times the sum of B plus C equals AB plus AC. This is the same if the multiplication is on the right. The sum B plus C times A equals BA plus CA. Just remember that the order matters here too. You have to keep the A in this circumstance on the right side. You can't swap them around once you end up distributing. Fourth, the identity matrix behaves like the number 1. A times the identity equals the identity times A equals A, as long as the dimensions are conformable. Fifth, the zero matrix sends everything to 0. A times the zero matrix equals the zero matrix, and the zero matrix times A also equals the zero matrix. So it behaves a lot like the actual number 0. Here, non-commutativity is the surprise. Everything else ends up working exactly how you'd expect from multiplication. Ruth steps back from the chalkboard. Victor now understands how matrix multiplication works, and he now knows how he can apply it to his own research. With Ruth's help, he's caught back up to where he needs to be in the program, and all he needs to get started on writing his own dissertation is a good idea. So that's matrix multiplication. Each entry of the product is just a dot product. The conformability rule comes from the inner dimensions matching. The 5 properties tell us how the operation behaves, and non-commutativity is the one that's different from how regular multiplication works. Matrix multiplication is going to not only be important for the rest of this unit, but also for understanding things like regression when we get to Module 5.